A single qubit superposition state is a quantum state in which a qubit can exist in two or more states simultaneously. In this state, the qubit is said to be in a superposition of the individual states. The superposition of states is represented mathematically as a linear combination of basis states, typically represented as Ket0 and Ket1. The probability of measuring the qubit in either of these states is given by the square of the absolute value of the corresponding probability amplitude. Superposition is a fundamental concept in quantum mechanics and is essential to the operation of quantum computers. The ability of a qubit to exist in multiple states simultaneously allows for the exploitation of quantum parallelism, which is the key to many quantum algorithms. In quantum mechanics, a qubit can exist in a superposition of two states that are not correlated, forming an orthogonal relationship. This orthogonal relationship can be represented using linear algebra as a two-dimensional vector in two-dimensional space. A single qubit superposition state can be represented as a linear combination of the basis states Ket0 and Ket1 using a two-dimensional complex vector. The coefficients alpha and beta are complex numbers, and the absolute values squared of alpha and beta must sum to 1. This two-dimensional vector representation is a common way of visualizing quantum states and is often used in quantum mechanics and quantum computing. By manipulating the components of this vector, we can change the state of the qubit and perform quantum operations on it. A quantum bit qubit state can be represented as a linear combination of Ket0 and Ket1. Since alpha and beta are complex numbers, they can be expressed in trigonometric or polar form. Complex numbers can be expressed in trigonometric form, also known as polar form. In this form, a complex number is represented as a magnitude r and an angle phi in radians. The magnitude represents the distance from the origin to the complex number on the complex plane, and the angle represents the direction from the positive real axis to the complex number. This trigonometric form can be written as r times the quantity cosine theta plus I times sine theta, where I is the imaginary unit. This form is useful for performing operations such as multiplication and division of complex numbers. A single qubit is a two-dimensional complex vector. Most of us learned linear algebra without complex numbers, but quantum computing involves complex numbers and linear algebra, specifically in Hilbert spaces. To simplify the understanding, we can convert complex vectors and matrices into their equivalent real vectors and matrices. When represented as a vector, we can expand each complex element into a two-dimensional vector, so a two-dimensional complex vector will be converted into an equivalent four-dimensional vector. Then, we can convert it back from Hilbert space to the real vector space.